In this video, we'll review the different types of chemical reactions. When we look at a chemical reaction, we can see we get a variety of different types of reactions. For example, if we have one compound, it can split into two, or we can take two compounds and make them one. We can also rearrange our ions depending on what we start with. All these different types of reactions have names to them. And if we know what type of reaction we have, we can predict what the products are. So looking at the first one we have ammonium chloride turns into ammonium plus HCl. This would be an example of a decomposition. Then we have zinc and chlorine, and we combine them together to make a zinc chloride. As you can see, it's a combination reaction. Next, we have zinc and copper chloride, which turns into copper and zinc chloride. For that one, we call it a single displacement. And then finally, we have silver nitrate and potassium chloride turns into silver chloride and potassium nitrate. That we call a double displacement. So these are our four main types of reactions that we're going to briefly look at. First, we'll look at a decomposition. In a decomposition reaction, a single compound breaks down into its elements or simpler compounds. So this usually occurs with heat. And so you can see here, we have a compound that contains 4 red atoms and 2 purple, and then decomposes into just 2 red atoms and 2 purple, and another 2 red atoms. You can see they're no longer combined together. Instead, it's split apart into its different atoms. We can say it got decomposed into its different atoms. So this is a general format of a decomposition reaction. You start with one thing and it creates 2 or more things. So when we predict the product for decomposition, usually it's hard to predict a product unless we know it decomposes into its individual elements. So this will be the key to see. It says it decomposes into its elements. If you see that, then you should be able to predict a decomposition product. So if I took platinum 4 chloride and it decomposes into its elements, you should be able to predict the product. So if we think about it, we have platinum and we have chlorine. So if it decomposes to its elements, the platinum and the chlorines should split apart from each other. And in fact, our platinum 4 chloride turns it into a platinum solid and 2 chlorine 2 molecules. Notice how the chlorine comes as chlorine 2 because that's its elemental form for chlorine. It's one of our diatomic elements. So when we have a decomposition, it usually decomposes into its individual elements, which means we can predict the product pretty easily. And most of the time, they need to be heated in order to have that happen. So now let's look at the opposite happening, a combination reaction. So in a combination reaction, you take 2 simple substances and combine them together to make a new compound. Combination reactions are not as straightforward for predicting as decomposition. And that's because these 2 individual compounds can combine together in different arrangements. So here we have 2 whites there together and 2 orange and 2 greens. They created 1 green, 1 white. What's to say they couldn't have done 2 greens and 4 whites? Kind of like our example on the other side. So when we look at our combinations, so most of the time when we have metals reacting with nonmetals, we can predict that product. So if I take aluminum and I react with bromine, you should be able to predict the product, because you know aluminum forms a +3 charge. And if it forms an ionic compound, you know you would need 3 bromines to balance out that +3 charge on aluminum. And then you can balance your equation afterwards. So if we have metal and nonmetal, and we usually form ionic compounds from that, you can predict the product. However, if it's 2 nonmetals reacting, then it's not so easy to predict the product. 2 nonmetals that react, can start to form different combinations as we learn from the nomenclature when we're naming our binary compounds. There's all sorts of combinations you can get. So in that case, two nonmetals, we can't really predict the product. Now looking at our single displacement reactions. In single displacement reactions, a free element displaces another element from a compound in order to produce a different compound and another free element. So essentially what's happening is one ion is switching partners. So here we have two green together and a blue. What's going to happen is one of the greens is going to attach to the blue and leave the other green by itself. So you can see one of the greens switch partners. Instead of it being two greens, now we have a blue and green. So that's the general idea with a single displacement, is one ion's going to switch partners. Typically, it happens to be the anion that will switch between metals. But that's not always the case. Here we have calcium and water. If I take solid calcium and I put in water, I'm going to get calcium hydroxide and H2 gas. Same thing if I have a chlorine gas. If I have chlorine and sodium iodide, I can get one of the chlorines to switch to create sodium chloride and iodide. So you can see in these two cases, I have one metal, but then the second one is a nonmetal. But there's still a single displacement because here my OH switched from the hydrogen here in water to calcium. And then when a metal reacts with an acid, we usually call that corrosion. So if I have pure iron and I put in HCl, I'm going to get iron chloride and H2 gas. So you can see the chlorine switch from having the hydrogen as a partner to having the iron as a partner. Now, in the process of a single displacement, we call this type of reaction an oxidation-reduction reaction, or redox for short. And that's because it involves a transfer of electrons between our reactants. So with a redox, you need to have an oxidation occur at the same time as a reduction. You cannot have one without the other. So what's going to happen is one atom is going to donate an electron to another atom. The atom that does the donation will go through an oxidation step. The atom that accepts the electron goes through a reduction. And so in order to remember this a little bit easier, the fundamental definition of an oxidation is the loss of electrons. The fundamental definition of a reduction is the gain of electrons. So a couple helpful mnemonics. You can have oil rig, oxidation is loss, reduction is gain when you're talking about your electrons. Or you can have Leo Gur, lose electrons, oxidation, gain electrons, reduction. And if we look at our example of the iron and HCl, the iron started as a solid. It had a 0 charge on it. And then with our HCl, each hydrogen has a +1 charge. Each chlorine has a -1 charge. Then when we look at our products, I end up with iron, I end up with iron 2 chloride plus H2. H2 is in its gas phase, that's its natural state, so now it has a 0 charge. Anything in its elemental form has a charge of 0. The iron now, since it has 2 chlorines next to it, is a +2, and the chlorine's still a -1. So you can see the iron went from a 0 charge to a +2, so the iron lost 2 electrons. If it lost 2 electrons, it went through an oxidation. The chlorine, you can see, stays the same. It's a -1 on the reactants, it's a -1 on the products. The hydrogen went from a +1 to a 0. So the hydrogen actually gained an electron. Since it gained an electron, it went through a reduction. So when you're looking at oxidation reduction reactions or single displacement, look for the atoms to have different charges from the reactants to the products. Like our example with the iron here. Iron has a 0 charge in the reactants, but now it's a +2. Its number of electrons changed. And you can see it went from being by itself to now it's partnered with the chlorine. So you can see that swap in a partner here. Next, let's look at a double displacement reaction. Double displacement is actually a really common type of reaction we have in chemistry. And in fact, it's kind of an umbrella for 3 different types of reactions. For our precipitation, our gas formation, and our acid-base reactions. All of these different kinds fall under the double displacement umbrella. And you can see what happens if we have our purple and our red, and our green and our white. What's going to happen is they're going to switch partners. So now we have purple and white and red and green. So since we had 2 partners switch, that's why it's a double displacement. And looking first at the precipitation reactions. Precipitation reactions and double displacement in general follow kind of this outline for how the reaction occurs. You have AX plus BY, and then they'll switch partners, give you AY plus BX. So if we recall our solubility rules, we can predict which of the products are going to be a solid and which one's going to be aqueous. So if you have silver nitrate and potassium chloride, they'll give you silver chloride and potassium nitrate. We learned in the solubility rules that silver chloride is insoluble in water, so therefore it becomes a solid. That's the precipitation part of our reaction. If I took these 2 liquids and mixed them together, I would get a solid out. And then you'd still have the potassium nitrate dissolved in your solution. But you can see how highlighted here, A is the same as silver, X is the nitrate, B is the potassium, and C and Y is the chlorine. And now you can see how they swap partners here. This idea of swapping partners and then one of the products is insoluble is the essence of our precipitation reactions. Next, let's look at our acid-base reactions. With our acid-base reactions, they follow the same idea as the precipitation. You still have that AX plus BY plus BY gives you AY plus BX. You still have that rearrangement, that double displacement happening. However, with acid-base reactions, one of the starting materials is an acid and the other one is a base, hence the name. Pretty obvious. And then whenever you do an acid-base reaction, you always get water. Water is always a product in an acid-base reaction. And then some sort of salt forms. So here, if I take HCl and sodium hydroxide and I mix them together, you can see the hydrogen is going to react with the OH to give you water. And then the chlorine and the sodium react together. And that gives you sodium chloride. And so the driving force for acid-base reactions is always the formation of water. If you see water as a product, you should start to really think, I did an acid-base reaction right away. Let's look in a little closer. As our example showed, we have HCl and sodium hydroxide, gives you sodium chloride plus water. So as I said, the products give you a salt plus water. That salt actually refers to any ionic compound. It doesn't have to just be sodium chloride, it's any ionic compound. And so if I have acetic acid and sodium hydroxide, I'll get sodium acetate and water. You can see it's still an ionic compound and water. So therefore, this one has to be an acid-base reaction. So even if you don't know the names of the compounds, you see water as a product and something that's ionic, you know you did an acid-base reaction. Now, going a little further with our acid-base reactions and still doing double displacement, we have what we call gas-forming reactions. And that occurs when we take a base and an acid, and sometimes we end up with a gas. So this is most common when we have carbonates and sulfites. So a metal carbonate, such as calcium carbonate here, when it reacts with an acid, it'll give you calcium chloride plus carbonic acid. So carbonic acid is the key. If you see carbonic acid, it's a very unstable compound. Carbonic acid will always decompose, another type of reaction we have, into water and carbon dioxide. So it's always going to decompose. And that's how you see where we get the water out, which means we still have an acid-base reaction here because we still have water as a product and something that's ionic. And that's also why if you take calcium carbonate and add it to acid, you get bubbles. And you can think of this and try it in your real life if you want. If you take vinegar, which is just acetic acid, and baking soda. Baking soda is sodium bicarbonate. We still have that carbonate. Even if it's bicarbonate, it still has a carbonate. That reacts together to give you sodium acetate plus carbonic acid. And that carbonic acid here will decompose to water and carbon dioxide. So if we took regular vinegar, which is just acetic acid, and baking soda, which I think everybody has in their own house, you mix them together, you'll get a lot of bubbles. This is how you make the classic volcano experiment for little kids. So if you want to go try it, trying your hand at a double displacement, go for it. Just make sure you're ready to clean up a mess. So that's our gas forming reactions where you have a carbonate or bicarbonate and it'll decompose to hydrogen carbonate. And it'll form carbonic acid, which decomposes to water and carbon dioxide. But we can still see it does our double displacement reaction first. So precipitation, acid base, and gas forming all do a double displacement reaction. Finally, looking at our last type of reaction is a combustion. This is typically what we call a fifth type of reaction because it doesn't really fall into any of the earlier categories. The closest we can do is put it under the oxidation reduction reactions. So in a combustion reaction, a substance reacts with oxygen and that burns to produce a flame. So we take some hydrocarbon, something that contains just carbon and hydrogens, reacts with oxygen, and then we get water and carbon dioxide as a product. So that means combustion reactions are easy to predict the products and easy to predict the reaction. If I tell you took some sort of hydrocarbon, so if you ever see something with carbon and hydrogens, that's it. You just see something with carbon, hydrogens, and I say does a combustion. You therefore know that it reacts with oxygen. Since there's oxygen in the air, there's plenty of oxygen around. And it'll do a reaction to create carbon dioxide and water. These are your two products. These are your only two products. So anytime you do a combustion, any sort of hydrocarbon will react with oxygen to give you carbon dioxide and water. And then you get a flame. One thing to note about this is all these phases are gas phase. So if you're trying to figure out what phase to write everything in for combustion, it's gas. Even the water is gas. And that kind of makes sense. If you lit a Bunsen burner, or if you have a gas stove and you lit the burners on the gas stove, you don't see a pool of water puddling up on the bottom. Instead, the water evaporates off into the atmosphere as gas. So kind of logically, we can figure out everything should be in the gas phase. And then looking at our reactions and a summary of our reactions, we have precipitation that we looked at, acid-base reactions, gas reactions, oxidation reduction, and combustion. Now you guys should be able to look at a reaction and determine what type of reaction it is, whether it's a combination, a decomposition, a single displacement, a double displacement, a combustion, whether it's an acid base or precipitation. Once you know what type of reaction you have, you can usually predict the products. As you saw, a couple of them you couldn't. Combination ones, if it's two non-metals, we can't really predict those. But most of the other ones, we can start to predict our products. So this way we know what we should get out of a reaction, what products we should get, so we can set up a reaction properly to figure out what we want and make what we want.